All right, a review from Wednesday. Okay, your test, first of all, your test is next Monday. So Wednesday, you're going to actually get some practice problems to take home today. And they're going to be due Wednesday. We'll go over them and we'll review for your test on Monday. So you want to go ahead and be studying for that. So, all right. So let's review. We talked about two types of chemical bonds on Wednesday. Does anybody remember what those two are? Ionic and covalent. Very good. All right. Ionic bonds have a large or a small difference in electronegativity between the atoms. Large. Okay, and so they're usually going to be a metal and exactly. All right. If we have, you guys fill in the blank here. Blank bonds have identical electronegativity values and are formed between two nonmetals. Okay, I heard covalent. What type of covalent? Nonpolar covalent. Okay. And polar covalent bonds have a different electronegativity values, but they are formed between two nonmetals. Okay. All right. Okay, so we're going to pick up where we left off. Okay. So we're ending our discussion on polar covalent bonds. Okay, and if we look here, we say that polar covalent molecules have a dipole. And this is represented by this symbol here. And all that's saying is that there is an electronegativity difference and there's a partial positive and a partial negative charge on either of the atoms. Okay, so HF, we have established that that's a polar covalent bond. Okay, we have a difference in electronegativity. We all know that fluorine is the most electronegative element. And so, sure, hang on one second. Okay, and so what happens is if we think about electronegativity, we know that the more electronegative atom is what is pulling on the electrons harder, right? So it's winning that tug of war that we had. Okay, and so the partial negative charge is going to be on the fluorine, which makes sense because it's pulling harder on the electrons, which are negatively charged. And so we show this little partial sign here, and then we show a partial positive sign here on the hydrogen. Okay, these are not full charges. Remember, for ionic compounds, we have full positive and negative charges. Okay, but for polar covalent bonds, they have a partial positive or negative charge. And basically it's just showing the electron density is pulled towards the more electronegative atom, which here is fluorine. We're talking about the charge and the pull of electrons. It makes it have a partial negative charge if it pulls the electrons because those are negatively charged. Yes, it's partial for polar covalent compounds. Yeah. Okay, so this is just a quick look. We're actually going to get into more detail, but I just want to go ahead and show this slide. We're going to get into detail later on. But ionic compounds versus covalent compounds. Okay, so we've discussed both of those to this point. And so ionic compounds are solids with high melting points. Okay, if we remember back to ionic compounds, they have, so let's say NaCl, a positive charge on the sodium, a negative charge on the chlorine. They have full charges, and so their attraction is a lot stronger. Okay, whenever the attraction is stronger, it makes the bonds harder to break. Okay, and so they're going to have higher melting and higher boiling points. Electrostatic interaction. It's an ionic compound if there's a large difference. Okay, and one thing we're going to learn in lab as well is that like dissolves like. Okay, and you may have heard this before, but what that means is if something is polar, it's going to dissolve in something that's polar. Okay, they have the same interactions. If something is nonpolar, it's going to dissolve in something that's nonpolar. All right, since electronegativity is based on polarity, ionic compounds. We have a metal and a nonmetal. So we have a large difference. Does that mean this compound is going to be polar or nonpolar? Very polar, right? We have a big difference in electronegativity. Okay, and so it's going to want to dissolve in polar solvents or other polar substances and be insoluble in nonpolar. And because they have these ions and this electrostatic interaction, they conduct electricity. And then the last one is the one that we'll actually see this in the lab here in a couple weeks, I believe. And the last one's what we've already talked about, that ionic compounds have different electronegativities between a metal and a nonmetal. Okay. Covalent compounds can be gases, liquids, or solids. Right? Ionic compounds are usually solids. They're going to have a strong, rigid lattice that they are in. And they are, many are insoluble in polar solvents, and it just depends because we have nonpolar covalent compounds and we have polar covalent compounds. So whether they're or not they're polar depends on the polarity of the atom or the bonds that we're talking about. Okay, and these typically do not conduct electricity and are formed between two elements with similar electronegativities. All right, usually nonmetals. Okay, this is also kind of review and kind of sums this up. If you know and understand this down here, then you have a good idea about everything that we've talked about in this chapter. Okay, you have two extremes. You've got nonpolar covalent bonds, and then you've got ionic bonds. Okay, and realistically, compounds kind of fall in between. They're really not all the way one type or all the way another. It's just the way that we try to classify them. We have to have a way of looking at them and being able to try to classify the different types. If you have a nonpolar covalent compound, so who can give me, well, there's an example up here, H2, okay, it's the same atom or element bonded with itself, and so it has a zero difference in electronegativity. Okay, so here we've got change, En. En stands for electronegativity. Okay. If it has a zero, then it is a purely nonpolar covalent compound. Okay. If electronegativity, the difference between the two atoms increases, then we have kind of our intermediate type of bond. And this is our polar covalent bond. So example would be HCl, HF, okay, ones we've looked at. Okay, and then if there's a large, and 1.9 is not always, that's what a lot of books say, but an electronegativity difference of 1.9 or larger is usually an ionic compound, okay, but not always. All right, and something like NaCl, this is a ionic compound and has a very large difference in electronegativity. Okay, and all bonds have some ionic and covalent character. Okay, so that's realistically how bonds exist, but we have to try to classify them according to this kind of scale for us to better understand the reactions that they will undergo. Okay, the next concept, and this is going to be what you guys have to go home and work on for homework, is it takes a little while to start picking up. Okay, it's we're going to learn to draw compounds. Okay, we got to know where to put electrons and draw the bonds and all of those things, and this is very important. So the first thing we're going to kind of do is we're going to go over rules. I'm going to talk through some things, and then we're going to practice. Okay, so just kind of listen to the rules, take them in, and then we're going to put them to use. Okay, you guys have kind of heard me talk about octet or the octet rule, and this just states that representative elements, which is what we're going to be dealing with, we're not going to look at things that aren't representative, usually want to attain a noble gas configuration. Okay, and we saw that when we've drawn orbital diagrams, and we've talked about that fluorine, for instance, wants to gain an electron to be like a noble gas. Okay, and so what we can do is we can represent atoms and their electrons by putting electrons around, and this is called a Lewis dot formula, or Lewis dot structure. And this is based on the octet rule. Okay. We also need to determine and look at compounds and see what electrons are bonding and what electrons are non-bonding. And this will make more sense when we start seeing some structures. Okay. All right. We use what's called the NASB method. All right. These rules are super important. And basically, it's a mathematical relationship or calculation in order for us to, it's kind of bookkeeping of electrons, basically. Okay, so you're trying to keep up with how many electrons does each atom have in its valence shell, and how is it going to bond. Okay, so the first thing we have to do is determine N, which is the number of electrons needed for an atom to achieve a noble gas configuration. Okay. For all elements besides hydrogen, this number is 8, all right, because all atoms need 8, hence the octet, electrons in order for them to have a noble gas configuration. Okay. If you have hydrogen, you remember it only goes to 1s2, right? So it just needs 2 electrons for it to be like helium, right? Its nearest noble gas. Okay, so N's pretty easy. This one kind of confuses people, but just remember, if it's any element other than hydrogen, it needs 8. So when you're adding these up, that's the number that you use. Yes, we're talking about, well, needed is just talking about what we need total. But available is going to be talking about valence. We're getting to that. All right. A stands for available. This is the available electrons in the outer shell. So this is the valence electrons. Everybody remembers that you can determine the number of valence electrons by looking at what on the periodic table? The group numbers, right? Okay. All right, and if you look at your numbers, you can go across. It just says A is equal to 8 for noble gases, which that makes sense. All right. S stands for shared. Okay, this is where we got to start looking at bonds. All right. If you take the number that you get for N and you subtract the number that you get from A, you should get S, which is the number of electrons shared in bonds. Okay, and this should be an even number. Why is that? Do you think? Right. What's a bond made up of? 2 electrons, right? Okay. Each bond is made up of 2 electrons. Okay. So if you come out with an odd number, you've done something wrong. Okay. All right. And B is just kind of repetitive for S, really. B is number of bonds. So if you take the number you get here at S and you divide it by 2, because there's 2 electrons in each bond, then you get the number of bonds that you have in your compound. Okay. I think this is our last page of rules. Yes, it is. Okay. For ions, we've talked about cations and anions. We know that if we have a 2+ charge, that we've lost 2 electrons, right? If we have a 2- charge, the atom has gained electrons. So we have to take this into account when we're drawing the structures, okay? And see how I've got this capitalized and some of it bolded, okay? You do not add or subtract electrons from your needed number, okay? If you have an ion, you add or subtract electrons to your available column or your available number. Okay, so that's your valence electrons. A lot of people make this mistake and they add electrons at the needed as well. Okay, and we'll show examples of this. Okay, and if you have a plus or a -1 charge, you add an electron, and for every negative charge, you add an electron. For every positive charge, you take away an electron. Okay, all right. When we start looking at compounds, for instance, well, we'll do some in a second, but you're going to wonder what is the central atom, what goes in the middle, and everything else branches around from it. Okay, the best way to look at this is to look at the least electronegative element. Okay, so whatever element is the furthest away from fluorine is going to be your central atom. Okay, and this is true for everything except hydrogen. Okay, hydrogen is never going to be in the middle. Okay, it only has one valence electron and it only needs one, so it's going to only form one bond. Okay, so it's never going to be in the middle. Okay, all right. So once you've calculated up your electrons, you're going to place your central atom in the middle, and then you're going to place the shared electrons. These are your bonds. Okay, connecting to the other atoms. Whatever additional electrons you have in your A or available column, you're going to place those as unshared electrons on every atom that surrounds your central atom. Okay, we're about to start doing practice on this. So, okay, and then if you have any left over, then they go to the central, any leftover electrons. Okay, and when you get done and you look at your structure, you need to add up all the electrons that you have shown. If that is equal to the number of A, or available electrons that you calculated, then your structure is more than likely correct. Okay. Also a hint, carbon always wants to make 4 bonds. Okay. So if you've got carbon, it needs to make 4 bonds, and it likes being the central atom. Okay. Okay, so we're going to practice this. Okay, so these are really simple ones, but let's look at F2. How can we draw F2? Okay, so the first thing, hang on. Okay. Okay, so the first thing, we're going to do our NASB method. So NASB. Okay. First we have to calculate the number of needed electrons. Okay. We have 2 fluorine atoms, both which are not hydrogen, and we said that every element besides hydrogen needs how many? 8. So for needed, we have 2 fluorines, each needing 8. So how many total will we have? Okay. All right. Available. Available is the same thing as looking at valence electrons. Okay. If we look at the group number for fluorine, it's in group 7. You've got 2 fluorines, so we should have 14 valence electrons. Shared. Now we're looking at shared electrons, or the bonds. Okay, shared is equal to N minus A. So 16 minus 14 equals 2. You have 2 shared electrons. So then if we want to look at B, which is all it is taking S divided by 2, that gives us 1 bond. Okay. We don't have to worry about a central atom here, right? Because we just have 2 of the same atom. So if we take fluorine and we draw our bond, all right, so we can put a check mark by that. We have 2 fluorines is what we're asked to draw. We have them represented here, and we have 1 bond. Okay? And we have 2 electrons shared, because those are kind of the same thing, just looking at it as electrons or as a bond. Okay. Now we look at valence electrons, okay? We don't have to go back and make needed as a checkpoint. We've got to have our 14 electrons represented in our structure, okay? And we know that atoms want to have 8 electrons in their octet. Okay, so if we start putting our electrons around, each fluorine now has 8. Okay, we've got 2 in this bond, 4, 6, 8. Okay, and 2, 4, 6, 8. Something doesn't look right here. Okay, I've never noticed for this one not to match up with the NASB method. Hang on. 2, 4, 6, 8, 2, 4, 6, 8. This is correct. So this should match up with 16. Fluorine's in group 7 times 2 is 14. I don't know why it's not matching up. No, I don't know why this one doesn't match up. That's really strange. I've never even, I guess we've just flown right past it. Okay. Right. Okay. Yes, it is Monday morning. Okay. 2, 4, 6, 8, 10, 12, 14. It does match up. Okay. But each atom has 8, okay, but if you look at it total, 2, 4, 6, 8, 10, 12, 14. Okay, wow. All right, moving on. Okay, so we've got N2. Okay, so let's look at needed for N2. I heard that. Okay. All right, so we need 8 times 2 again, right? Okay. Okay, it's in group 5. Okay, so it's 5 times 2. Okay. All right, so if we calculate our S, what should we get? Okay, so if we divide 6 by 2, we get 3 bonds. Okay. All right, so if I'm going to go up here. And remember that your structure has to match up with the number of atoms that you're given. You can't start drawing different things to make your bonds match up. I get that a lot, surprisingly, that they'll add another nitrogen or something. Well, you can't add any more atoms than what it's asking you. Okay. Okay, so the first thing we can look at, I like to start with bonds. So right now, we know we have 2 nitrogen bonded together, but we only have 1 bond shown. Okay, so if we've got 3 bonds that we need, what are we going to need to do? No, remember we can't add atoms. Okay. Okay, if you need more bonds than you have atoms, then you're going to have to start showing double or triple bonds. Okay. So now we have 3 bonds. We can check that off. Okay. And we have 6 electrons shared because each of these counts as 2, so 2, 4, 6. Okay, and now we need 10 electrons available. So if we put here, okay, you guys count this up for me since I can't count today. Does everybody get 10? Okay, we've got 2, 4, 6, and these are bonding electrons. Okay, and then we've got, these are called non-bonding electrons, or I call them lone pairs. Okay, and so we've got 2 of those, so we've got 2, 4, 6, 8, 10. I can count. There are exceptions to this rule, and that's what threw me for a second when I wasn't counting right, because there are exceptions, but I'm not going to test you guys on exceptions. Okay, there's exceptions to lots of rules in chemistry, but I want you guys to learn what's not an exception. And I was thinking this cannot be an exception, but I just need to count. All right. We're not moving again. Okay, so we'll show that there. Okay. Now let's look at HF. So now we've got 2 atoms that are different. Okay. So we still got to do, I think. Okay. So we're still going to do our NASB method. All right. We've got fluorine, which we know needs 8. We've got hydrogen that needs how many? Only 2, right? You don't want to have 8 there. So this gives us 10 electrons. Yes. Yep, it only needs 2. Okay. Okay. If we look at the available electrons for fluorine, we've already said that was 7, right? Okay, how many available electrons do we have for hydrogen? 1. Remember to put 1 here. A lot of people accidentally put 2 here. Okay, remember that hydrogen only has 1 electron in its valence shell.
Why is hydrogen too much?
Because all it needs is 1 electron to be like helium, its nearest noble gas. All the other atoms have to have 8 elements. Okay? 10 minus 8 gives us 2. And if we divide 2 divided by 2, gives us 1. Okay, we just divide by 2 for how many electrons is in a bond. All right, so I've already got it up here for us, but we would do this. And we've got 1 bond represented and 2 electrons shared. Right. Now we have to place, so we only have 2 electrons that are represented and we need 8. Okay? So we've got to add in our non-bonding electrons. Okay, so we've got 2, 4, 6, 8, and that matches up with our 8 here. Okay, you will never, ever see this. Okay? Hydrogen only wants 2 electrons and will only make 1 bond. Okay, so if you put 8 electrons around hydrogen, that is not going to happen, and I honestly cannot think of an exception to that. Okay? So hydrogen is always going to be no non-bonding electrons on it and can only make 1 bond. Don't know why it's not flipping for me. Okay. Now we're going to do these 3. Get a little bit more complicated as we go. Okay, so we're going to do water, H2O. So we need needed. Oh, every time. Okay. All right, we've got one oxygen, which needs 8, right? And then we've got 2 hydrogens, which needs 2. So that gives us 12 electrons needed. Okay. Now we're going to look at available. We've got 2 hydrogens, and they have 1 valence electron. And then oxygen is in group 6, so it has 6 valence electrons. So that gives us 8. Okay. Now if we're going to look at shared, we take needed minus available, which gives us 4. And then if we divide that number by 2, it gives us 2 bonds. Okay. Okay, so we've got 2 bonds, and we know that hydrogen is never going to be the central atom. So that leaves oxygen to be the central. Okay. We've got 2 hydrogens. Okay. So we've got our 2 bonds shown. Okay, remember this has to match up with the number of atoms you've got in your problem. And then you have 4 electrons shared, so you've got 2, 4. No, yeah, you can write it with the bonds here. But you can represent it either way. Okay. So here we have 4 electrons represented, but we need 8. Okay, so where are these electrons going to be placed? Okay. They cannot be placed on the hydrogen, right? Okay. So we have a pair here and a pair here, and these are our lone pairs. So now we have 8 represented electrons, so we can mark that off. All right, if we look at ammonia, nitrogen needs 8 electrons. Hydrogen needs 2. And we've got 3 of those. Okay. Hydrogen is in group 1, has 1 valence electron, and there's 3 of those. And then nitrogen is in group 5. So we have 8 available or valence electrons. We subtract 8 from 14, we get 6 shared electrons. Divide that by 2, because there's 2 electrons in every bond, we get 3 bonds. Okay. So we've got a nitrogen in the middle, and we've got 3 bonds, and we've got 3 hydrogens, so it works out perfectly. Okay. We have 6 electrons represented, and we need 8. So where are the 2 electrons going to be placed? Yes, ma'am? Oh, that was probably supposed to be a plus. Sorry. Yep.
So for going back when we did nitrogen 8 was supposed to be added, not multiplied, right?
Up here?
Oh, okay. Okay, I get it. I got it. No, I was talking about nitrogen, but they said it was supposed to be the same element as multiplied.
Okay. All right. So if we look here, we've got 2, 4, 6, 8, and we need 8. So we are done. Check this off. Okay. If we have the ammonium ion, so we're going to do one that has a charge. Okay, it has a +1 charge, and we know that if it has a +1 charge, then you subtract an electron. Okay. So for needed, we need 8 for nitrogen, plus, not times, plus we need 2, and we've got 4 hydrogens. So 8 plus 8 gives us 16. Okay. Available, have 5 for nitrogen. It's in group 5. We've got 1, and we've got 4 hydrogens. Okay. All right, but we can't stop here, right? Because we've got to add or subtract. If we have an ion, we have to add or subtract here. Okay, so if we were to calculate this, we would get 9. And remember, we said we can't have an odd number of electrons, right? So are we going to add or subtract here? An electron. Right, so we're going to have -1 electron. Okay, so that gives us 8.
Yeah, so this is negative. It's more negative.
It's got a positive charge, meaning it lost an electron.
At 9, that's positive. How much?
What do you mean 9?
That
5 plus 4 is 9.
because that's a plus, you'd subtract one.
You subtract an electron because it lost an electron. Because it's positively charged. Okay, so 16 minus 8 gives us 8. And then that gives us 4 bonds. Okay. So we have 4 hydrogens. We can make our 4 bonds. Okay. All right, so if we look at our valence, we need 8. And how many do we have represented? 8. Okay, the only thing left to do is whenever you have something that has a charge, you want to put it in brackets and leave it with that positive. Sorry, you can't hardly see that, but okay, because the atom is still, we're drawing a positively charged molecule, right? So you got to be sure you still represent it as positively charged. Yes. All right, now I want everybody to do this one. It's negatively charged, so be sure you remember to add electrons. This one you've got to figure out which atom is the central atom. So don't forget about that rule. Okay, what did you guys get for needed? 32. Okay, so we've got 4 atoms, all of which are not hydrogen. So we need 8 times 4, 32 electrons. All right. Available, we look at valence electrons here. And so we see that sulfur is in group 6. And we've just got one of those. Okay. And then oxygen is also in group 6. And we've got 3 of those. Okay, so that should give us 26 electrons.
Then you got to add 2.
Oh, sorry. Oh, yeah. Okay, so eventually we're going to get 26. All right, so then we've got to add 2 electrons for our charge. We've got a 2 minus charge. We've got to add 2. So that gives us 26. Okay, so if we take N minus A, so 32 minus 26, get 6 electrons that are going to be shared, and 3 bonds. Okay. All right. Which atom is going to be our central atom? Sulfur. Okay, it's our least electronegative element compared to oxygen. Okay, we've got 3 oxygens. Okay. I get a lot of questions about the geometry, so some of you may have drawn it like this. Okay. You guys haven't learned the correct geometries to draw them in yet. I know them, so I draw them in the correct geometry, but I won't count off if you don't at this point. Okay? Because you guys haven't learned that yet. Okay. So we've got 3 bonds. We can check that off. We've got 6 electrons that are shared in our bonds. Okay. And now we need 26 electrons. All right, and we've only got 6 shown. So this is our rule where you add electrons to the atoms that are branched off of your central atom first. Okay, so you don't add to sulfur yet, and you may not have to in some situations. Okay, so we add here. So we've got to add 6 more electrons to give 8 to oxygen. We've got 8 there. 8 there. Okay. All right, so that gives us 24. Okay, now if you still have leftover electrons, then those are going to go on your central atom. And that should give us 26. And then we put this in brackets with our 2 minus charge. Depending on if you have non-bonding, okay, see how you have these lone pairs here, okay, they dictate the geometry, okay, so it's really a whole 2 or 3 lessons talking about geometry. You guys do not right now. They actually have, we don't even do the lab that we used to on it, but this becomes really big in like organic chemistry and stuff. Yes. Okay, it's the furthest away from fluorine. Yep. Okay, and the last thing we're going to talk about is something called formal charge. And basically, sometimes you're going to run into a problem where you may need a double bond to one atom, and you're not sure which atom it goes to. Okay, you've got two different atoms, and you're not sure which way your double bond should go. And we're going to show an example of this. For the Lewis structures that you're drawing, you're trying to draw the most stable structure that there is for that molecule. Okay, and so if you have a structure where the formal charge, we'll talk about what that means in a second, is 0 for all the atoms represented in your structure, then it's more than likely the most stable structure for that compound. Okay, formal charge is equal to the group number, so it's talking about the group number on the periodic table, minus the number of bonds, okay, for that atom, how many ever bonds it's making with another atom, plus the number of unshared electrons. Okay, so these are our non-bonding electrons. Okay, so let's look at this example. So I want everyone, I know I've got it represented here, but I want everyone to do the NASB for NOCl. Okay, so write your NA, calculate up your available. Okay, remember that the least electronegative goes in the middle, so it's going to be nitrogen. Okay, so if we look at the number of needed electrons, we've got 3 atoms that are not hydrogen, so we would have 8 times 3 is 24. Okay. For our available, we've got nitrogens in group 5, plus oxygens in group 6, plus chlorines in group 7. So that gives us 18, right? So we have 24 minus 18 gives us 6 shared, or 3 bonds. Okay? So this is where we run into a problem. So once we draw nitrogen, okay, we know it's in the middle because it's the least electronegative, okay, but we need 3 bonds, okay, so how do you know whether to put your bond over here or over here? Okay, because technically there's 2 ways that we could do this, okay, and so if we draw it this way, so if we put our double bond here and we add electrons around, this is what we get here. And this will should match the number of available we need. So 2, 4, 6, 8, 10, 12, 14, 16, 18. So this matches our available. All right, 2, 4, 6, 8, 10, 12, 14, 16, 18. This structure also matches our available. Okay, this one's going to be very similar to the last problem on your homework. Okay, so you've got 2 structures that it could be. You've got to determine which one is more stable. This is where you calculate the formal charge for each atom. Okay, so if we calculate the formal charge for chlorine here, you take the group number, so chlorine's in group 7, minus the number of bonds, so here we have 2. That's connected to chlorine, plus the number of unshared electrons. So we've got 2, 4. Okay, that gives us a formal charge of +1 on chlorine. Okay, for it to be the most stable structure, we want it to be 0. Okay, so I'll go ahead and just tell you this one is the one that is favored. If you do that for every atom, so if we do it for chlorine in this structure, we've got group 7 valence electrons minus 1 bond plus 6 unshared gives us 0. Okay. If we do the same thing for nitrogen, it's in group 5 minus 3 bonds. We've got 2 here, we've got 1 here, and it's got 2 unshared, gives us 0. Okay, so this gave us 0 for both sides. Okay, if we do it for oxygen over here, we get a -1 charge, and we get a 0 over here. Okay, these total up to give you a +1 and a -1 to give you 0. I realize that, but for these, your formal charge is 0 for every atom. Okay, so this one would be what would be favored. So formal charge is equal to group number minus number of bonds plus number of unshared electrons. Okay. Let's see, no lab this week. If you have missed lab or you have not turned things in, at this point I don't know if I'll take up homework and things without I think late penalty is about over. But yes, yep, I'll give you guys out your homework and be studying, and we'll review on Wednesday. So all of you should have studied and be ready for the test by Wednesday so you can ask questions.
It's further away. It's in group 7. Wouldn't you know to put the ball